Welcome to GeoAI with imagery and 3D data. My name is Pavan Yadav. I'm a product engineer with the imagery team, and at Esri, I focus on imagery and AI. Agenda, this is going to be a demo-rich session. We will have a quick introduction, then we will talk about the pre-trained models, the tools, then Python API, 3D deep learning, and how to integrate third-party training data and models into ArcGIS. Then we will talk about what is road ahead, key takeaways from this session, and then we will open the floor for questions and answers. ArcGIS's evolution into geospatial AI platform is built on 4 key technical pillars: GeoAI, AI assistants, AI agents, and unifying AI framework. Each component plays a distinct role, from advanced AI-powered spatial analytics to intelligent user interfaces, workflow automation, and robust infrastructure that unites everything together. GeoAI is AI-powered spatial analytics to extract information and analyze data. AI assistants are generative GIS co-pilots. They are designed to improve access, efficiency, and productivity across all of ArcGIS. And lastly, the AI agents enable agentic or intelligent workflows. In this session, we are going to focus on GeoAI. GeoAI is really the culmination of geography and AI. It integrates deep learning and other machine learning techniques into GIS to automate analysis and uncover spatial patterns. GeoAI advances the science of GIS by using AI to extract data and analyze data. This is done by 2 key things: feature extraction. We use computer vision techniques on imagery, 3D data, and video to extract features such as detecting cars or detecting elephants or classifying land cover. Then we use natural language processing on unstructured text data to get meaningful information. So that is about getting information from imagery or text data. Then the second aspect of GeoAI is advanced analysis. We apply machine learning and deep learning on various kinds of data to do advanced analysis. Again, this session is about extracting features from imagery and 3D data. On this screen, you see various data modalities for 3D and imagery. In the boxes, we have different kinds of data types, such as 3D scenes, point cloud, overhead imagery, oriented imagery, motion video, which is video really, motion imagery, time series data. When we talk about imagery, not just true color images, we support multispectral, hyperspectral. And when we talk about oriented imagery, it's really, we are talking about drones, images captured by drones or car-mounted camera or maybe handheld cameras. Against these data modalities, we put together some examples. For instance, for 3D, we support object classification and object detection. For imagery, we support object detection, pixel classification, object classification, change detection, and so on. Now let's look at how GeoAI is provided in ArcGIS. At the foundation, we have the ArcGIS Learn in Python API, giving developers and data scientists granular options for GeoAI workflows. On the other hand, our GIS users are more familiar with the geoprocessing tools, so we support full GeoAI with the geoprocessing tools as well. And for those who just starting their GeoAI journey, are ready to use pre-trained models, provide the perfect entry point to take advantage of GeoAI immediately. Depending on your business need, you use these 3 to build apps and solutions. Now I'm going to hand over to Priyanka, and I'm sorry, Priyanka is going to introduce herself and
well, hi everyone. Today, like Pavan gave us an introduction to what GeoAI is, how it's layered. So at the core, we have the ArcGIS Python API, followed by another layer where we have ArcGIS API for Python, followed by pre-trained models, tools, apps, and APIs. I will focus first on the pre-trained models. And before that, I'll give a quick introduction. So my name is Priyanka, and I work as a product engineer at Esri R&D Center, and I'm very focused on pre-trained models and understanding how we could really extract meaningful features and extract information from different types of input imageries. So here I'm focused on pre-trained models. So let's begin. Apologies for this glitch.
Can you extend your screen? Sorry about that.
Okay, so to start with pre-trained models, how many of you already know about what pre-trained models are? Any idea? Well, I guess everyone in this audience knows about pre-trained models, and many of you may be already using a lot of these pre-trained models. So the names that you see on the screen right now, some of them are, task-specific models, and you could just understand what they do by their name. So car detection, crowd counting, building extraction, road extraction, and some of the new models here that you read as, for example, grounding dyno. I don't know what it does, right? Vision language context-based classification. And some of these are really models which can do a lot more than what you may be even thinking. So some of these models, they act as a starting point for all of you within the larger GeoAI workflow, but for others, it can also serve as a complete AI solution. And for some of these industries where these models can really solve a lot of problems, let's look at these examples. So here we have a story map, and we are showing how different domains and industries can apply these models and can solve problems. So one of these examples is optical character recognition, how you could use a model which is already there and figure this out. We have landcover classification. So these are examples of models which users can use directly, and state government and local government can use directly to maybe do infrastructure mapping. Similarly, for public safety, we have models. For example, this drone detection. So, if there's a disaster and there is some help needed to really figure out where to find these humans and help them rescue. So this is a model for public safety. We have few other models for utilities, natural resources. So if you look at this example, this is solar photovoltaic park example, where we can easily figure out and segment these areas. Then we have models for conservation as well. So this is a seabird detection example. And now these are task-specific models. So you can easily figure out that, okay, this is a seabird detection model, and of course it does this. But there is also a category of foundation models which is generalized in nature. So you can make it do anything you probably would like to, but you'll have to just let it know in a prompt, in a way, in a natural language, by just writing what you would like it to do. For example, you can ask it to detect whether these buildings are damaged, minor damaged, major damaged, or undamaged. So providing simple prompts can just solve the problems in a generalized way. You don't require specific models for everything. Now, where do you find these pre-trained models? You can find these pre-trained models on the Living Atlas. You only have to go to this all content types, and the ArcGIS provides a suite of tools and apps and APIs, but it now also provides a comprehensive list of these deep learning packages. So we have almost over 100 pre-trained models available. You can read by the card names that there is a mix of categories. We have task-specific models. We have some generalized models. And I can open one of them quickly just to show you how it looks like on the item page. So this model shows its detailed description. It shows how you could use this model, what is the input that is required, what kind of resolution is this model trained upon, what was the model architecture behind this, and the sample results, how it works in different areas. So as I said that we have categorized these models into categories. So it can be task specific, it can be generic. How does generic model really help your use case? It really makes AI more approachable. So all of you don't need to really understand deep, complex, AI concepts, and you can just simply type in what you want to do. You could say, what do you see in this imagery? And the model will tell you what it sees. You might just say, please delineate these water bodies, and it will do the job. So that's how it's very easy nowadays with the era of foundation models and natural language models, which can easily be used by just providing prompts. And next, I'll show you another story map where we'll look at some of the examples of these models. For example, this one is a nice one. I like this one. This is image interrogation one. So in this, literally, I asked the model to tell me, what do you see in this image? And it did say the image shows a marina with several rows of docks filled with boats or yachts. Adjacent to the marina, there is a large building complex with a distinct architectural design and a pool area. And you could really see that it's there. So this model really works. Then we have models, for example, this is again another generalized model, which is grounding dino. And you just need to provide it a text prompt saying, just figure out planes. So just type in airplanes, and it will extract all of these planes with a bounding box around all of them. Similarly, we have models that can do segmentation. So like I've got this water mass extracted by just asking it to do the same. And then there's a new category of models. You see all of these model names have some HF as an initial. What that means is hugging face. So we have created these models as bridge to connect to all of these user contributed models that exist in the hugging face community. So you can get any of the model that you would like to use, but just provide a hugging face ID, and that's it. You will be able to use all of these open source hugging face models within ArcGIS ecosystem. One of the examples that I like to show is this one. So here, this is an imagery showing 2 swimming pools, but I just wanted to check that this model really works. And so I asked this question, how many pools do you see in this imagery? And it said 2. So it really worked. These are some of the examples where how generalized models can do multiple things. Now, some of the examples of task specific, and I think many of you would already know, but just to give you some overview of what it looks like. This one is an building extraction example. I think I'll just open some of these that I really like. So this one is pedestrian infrastructure classification. It can classify the curbs, the sidewalks, and another is maybe parking lot classification. This one is, again, you can see it can classify all the parking lots. So these are some task specific ones. Now, all of you have heard about pre-trained models, and you may be thinking, which one do we choose? There's so much. There is task specific, there is generalized, and even in the list of generalized, multiple models can do the same task. There are so many things that we could do and play around with, but because it's all based on the text prompts. So how do you make the decision? What do we choose? So the comparison is here. On the left, you see task specific pre-trained models, and on the right, you see generalized ones. So the task specific models can work on different kinds of imageries, the image sources. It can work on SAR, it can work on Sentinel or Landsat, but the generalized pre-trained models at this state, they only work with RGB, 3-band data, natural images. The second point is the accuracy. Because it's task specific, it's obviously going to work really well in doing that specific task versus some model that is doing multiple jobs, because it does multiple jobs, it just compromises on the accuracy a little bit. So what is more accurate? Whether your task, what you want to extract, whether your priority is to get more accurate results, or your priority is to just check if your model works and you can just do a little bit of post-processing and get things done. So in terms of accuracy, task-specific models have higher one. Coming to the supported data types, as I said, task-specific, it works on Sentinel, it works on point cloud. We have support for bathymetry, we have support for SAR, but generalized, as I said, they work on true color pictures. Next is the kind of tasks it can handle. So geospatial models, for example, generalized models like vision language context-based classification model, they are not trained on geospatial data. So they're trained on non-geospatial data sets. But just because we are able to integrate that into ArcGIS systems, we are able to utilize the power of non-geospatial models as well into the geospatial systems. However, the task-specific models, they are definitely trained on data sets that come from satellite data. Next is the model size. So that is very important because all of you work with different GPUs, and you take a model that takes just 3.5 gigabytes of space and it does the job, versus another one that takes 24 gigabytes, and you're like, oh gosh, it just crashes because it just consumes all the GPU that I might not even be able to use that. So coming to, when you have a task which can be solved with task specific, try and go with that, because that's going to consume less GPU consumption, versus something like a generalized model will consume a lot of memory, because they are large language models. They consume a lot of memory. Next is fine-tuning. We can always fine-tune task-specific models. Something, for example, I have a building footprint extraction model and I have it for a US geography, but I want to train this one for maybe somewhere else where the pre-trained model doesn't exist. And I can fine-tune that. I can just provide it a training label of maybe around 100 training chips, and I can say, hey, train the model on this new extent, on this new geography. But the generalized models, they cannot be fine-tuned. They are just trained on billions and billions of data, and that's how they work. They're not fine-tunable. Well, I think, yes, here we end with pre-trained models story map. I'll go ahead next the PowerPoint. Next, you see an example of how we do this demo and show you really the power of using these pre-trained models to solve one of the problems which is very critical. So let me open ArcGIS Pro. Here, I'm showing an example where Jamaica was hit by Hurricane Category 5, meaning that, post-disaster, there was huge damage. And you could look at that here. Now, I want to use this imagery and want to do operational insights. So I want to convert my imagery into operational insights. I want to turn the data into action. So it can be used by governments and agencies to solve their problems and provide aid and help needed as required. So what I do is I get an area of interest. Here is a helicopter landing zone, and I have two places where I want to provide aid, a hospital and a relief tent. So what do I do? Because of the hurricane, all of this has damaged. There may be roads which are damaged, and there is the pre-existing road data. I cannot rely on that because it may be they are flooded. It may be that they have major debris. There is no way to walk through that. So because we cannot rely on pre-existing road data, I went ahead and used the road extraction global model using the detect objects using deep learning tool that exists in this ArcGIS Pro. So if you look for detect objects using deep learning, here is the tool. You could just provide your raster here. So whatever is my raster, I provide that here. I have given that and I select this model. So I can look for, a road extraction model and just simply searching that and saying, okay, I will be able to load this model and show all the model arguments and then hit run. So that is how I got these results. In the sake of time, I'm not running it as of now. Once I had these road features, I wanted to really understand what is it? Are these roads even usable? Can I literally provide aid to those two locations, the hospital and the relief tent, from the helicopter landing zone? And so I performed another model. I ran another model on my roads features. And what that was is that I used classify objects tool. And I provided these input features as the road features, and I asked it to classify the road features into these classes: completely blocked, minor debris, major debris, or clear. And I also asked it to provide the context. Say it's imagery that is coming from a hurricane after a Hurricane 5, and I just hit run. And that is when I get these results. And it shows clearly the roads that have minor debris, the roads that have major debris, and the roads that might have been completely blocked. Looking at this example, it shows a road which is flooded. So this is no longer accessible and we cannot use this. And so using this updated road network, I performed routing analysis and I was able to find the optimal paths to reach both of these locations from this helicopter landing zone while avoiding blocked roads. This is how I used pre-trained models to solve a problem and get operational routing. That is one example. So I clubbed a task-specific model, which was road extraction, and a vision language context-based classification model, which was a generalized model, to solve this problem. Next, I had these building damaged roofs. You can see many of these roofs, they have holes and decks. And I want to find out how much is the damage, whether there is a severe damage, whether there is a minor damage, and that can help insurance companies provide insurance based on the kind of the severity of the damage. And so I tried out 2 user-contributed models. I'll show these models to you. So here are these models, the roof decking delineation and roof hole delineation. And I tried them out, and trust me, it did not work. So it's not that always you go ahead and find a model on the Living Atlas and it would work out of the box. But how I solved my problem was that I fine-tuned this model. So I literally labeled 50 labels, 50 samples of this manually, and exported the training data using the export training data using deep learning tool. So if you look at this export training data, there is this tool. So I provided my raster and I provided whatever I had labeled. And that's it. I was able to export the training data, and then I went ahead and fine-tuned the model. So here's the notebook. Using the ArcGIS Python API, I was able to import the model which I was interested in fine-tuning. And because this model was already trained, so if I go back and I check, hey, what was the model architecture? How do I know how to fine-tune this? So you can see here, the model architecture here says mask to former. It's coming from ArcGIS Python API. It's part of an segmentation class of models. And using this, I fine-tuned my model on this post-disaster imagery. And within 30 minutes of training, I was able to get good results. And that's when I applied inferencing of the model that I was able to fine-tune and get these. And it really worked. It's not that it did not work, it just needed a little bit of fine-tuning. So that's an example of how you could use models right out of the box, or might need to fine-tune these models to make it work on your area or your extent. With that, we'll pass it on to Pavan for the next.
Thank you, Priyanka. By the way, we have about 110 pre-trained models, not just for imagery, but also for text and 3D. Okay. Priyanka did so export training data tool and the tools that we use to use the models. Now let's look at another aspect of GeoAI. So even though we have about 110 models, there could be scenarios when these pre-trained models do not meet your business need, and you might need to train your own model. In ArcGIS, Image Analyst, 3D Analyst, Full Motion Video, Deep Learning Studio, and API, they allow you to use these GeoAI tool not only to use existing models, but to build the training data and build models and use them. ArcGIS is really an end-to-end geospatial AI system. On the top, you see data coming from various sources, and ArcGIS provide very good solution to manage those data. Data might be coming from drones, satellites, various kind of sensors or cameras. Then we have full GeoAI system, and it is augmented by powerful QA tools. Once you have layers from your GeoAI workflow, ArcGIS offers over 2,000 geoprocessing tools. There seems to be a problem with the recording. Okay. So once you have output from your GeoAI workflow, you can use over 2,000 geoprocessing tools to post-process them. And once you're happy with the quality of post-processed data, you can share them with your audience, maybe using ArcGIS Online or StoryMap or other ArcGIS app. On the following these slides, we are showing how you can prepare data, label them, and build models. Again, powerful QA tools support them, then consume and deploy them, and use those models at scale. Next, I'm going to show you a demo. Okay. Can anyone guess what these guys are? So we are in Atlantic Ocean near the west coast of Spain in Europe. And if I zoom in a little bit, I see these. These are mussel farms. Mussels are sea creatures, animals that are consumed by millions of people. And for my area of study, I would like to build a model and use it. And what I'm going to do is I'm going to start with creating training data. To create training data, I come here on the imagery tab and open label objects for deep learning tool. It opens this interface where I already created a class, and now I'm ready to create labels. I'm going to use this AI assisted label tool called auto detect, but you can also use other tools or you can use prompt based tools. When I click, these are my labels. Really, to build a model, I need an image and labels. But 4 samples are not enough. My coworker has created samples for me. And what I can do is I can bring those samples here in the QA tools. And this is something, by the way, new at 3.6. And you can go to this interface using review, labels, and training data. And I'm going to bring the labels my coworker has created for me. And I can check the quality of the data. I can approve, reject, I can take various actions. But because I trust my coworker and the the labels look good too, I'm just going to accept all and go for the next step. However, what if you have thousands of samples, maybe 10,000? It's not possible to manually review them, and that's why we provide you auto review. In that tool, you can input labels and ground truth and generate a report. Now that because I'm happy with the quality of data I'm provided with, I'm just going to use that. I said all you need an imagery and labels, but there is a catch. You can't just input this large image into deep learning. You have to split that image, and that's where the export training data tool comes into the picture. What this tool does, it chops up the image into smaller pieces, and all you need to do is input the image and the label, set the size of the chips, and if you want overlap, and set the right metadata type. In this case, Pascal VOC is the right one. Once I export the data, I would like to review if the quality is good. To review that, I go to the data tab and bring the exported data. Here it is. I can I usually like to just set a speed and then play buttons and to see like how they are looking. But I have other options like filter, jump to, jump by. In this case, because I'm happy with the quality of exported chips, I'm ready to train a model. In the interest of time, I have already done all these. On this laptop, it took about 50 minutes to build a SSD model. It's one type of architecture for object detection with 20 epochs. However, I was not very happy with the quality of this model, and I'll show you why. So I tried again, and this time I used detection with 10 epochs. Now that I have two models, I wanted to compare the two. For that, I opened this model reviewer and brought the two models that I have built. When I bring one, I can see its report, and let me add the second one as well. So I can go back and forth and look at, or I can click on this guy to generate a compare report. The compare report is an HTML file, and this is how it looks. I'm interested in average precision. The second model gives me 98% precision versus the previous SSD model was giving only 65. So now that I have a good model, which is detection one, I'm going to use that. To use the model, I will use the detect object tool, input the image, the model, and intentionally I did not change any parameters so that I can show you the other tool. Anyways, when the tool finished, and I ran that model against this test data, and test data is actually a mosaic data set, and here are my detections. Look really good, but let's go closer. So when I zoom in, from the higher level, it was looking good, but I see some false detections as well as a lot of duplicates. Because I have ground truth samples already for this, I ran this tool called Compute Accuracy for Object Detection. This tool takes the detected objects as well as my ground truth and generates a report as well as it generates table. This is a report, and here I can see there are actually about 60 harms are correct. I know that, but there are false detection, false positive, which is about 62. So the report confirms what I suspected. There are a lot of duplicate, and this is a very typical problem in object detection. And the way you handle it, you use non-max suppression. I did not do it because I wanted to show this tool. But once I know the problem is there, I ran non-max suppression twice with two different numbers, and finally I was able to get very clean data. So it is looking good. Let me zoom in again. So duplication is removed, but there are object false detections. And I think what I wanted to highlight is, first thing, there are three unique steps. One, prepare data, build a model, and use it. That creates your first prototype. Then you have powerful QA tools to check the quality of each step and fix. And I guess this is an iterative process, and you can continue to improve your GeoAI workflows. With that, I'm going to hand it over to Priyanka, and Priyanka is going to walk us through Python API.
Well, just giving you an overview. We talked about pre-trained models, we talked about tools, and now we're talking about the core, which is the Python API, the ArcGIS API for Python. Many of you who are developers and data scientists, they need to work with GeoAI programmatically, and they want to enable ArcGIS API for Python so that they can run their workflows in an automated fashion and could scale deep learning workflows. So let's get started with how you could do this. Why ArcGIS Learn? ArcGIS Learn leverages the high-level capabilities of fast AI, which is already itself built upon a powerful PyTorch library. In just a few lines of code, you could see that we could run ArcGIS Learn workflows. But if you look at the left, it's large, complex code. So with this layered architecture, ArcGIS Learn allows us to execute complex code within just 5 lines of code, and that too without requiring to learn about the deep AI concepts or the complex concepts. And that is why we chose to have ArcGIS Learn as our Python API to solve the problems using deep learning. Now, where do you find deep learning? Where do you find ArcGIS API for Python? So here, if you look at developers.arcgis.com/Python, we have this site. Let me quickly hop on to that. And here you see API reference. So what I earlier showed you was this API, was this developer site. And we have two options here. There are samples and there are API references. And I'll walk you through both of them. In the ArcGIS API for Python, it is ArcGIS Learn, which is the heart of the deep learning. This is where everything is coming from. Even in tools or pro or pre-trained models, it's all coming from this API. And you can see here a lot of modules, sub-modules. You can see automated machine learning, automated deep learning. You could see object classification, object detection, pixel classification, and a lot more. And when you expand them, you will find out a huge list of model architectures that we have integrated and provided it to all of you. So you could directly choose. You have the flexibility to choose, hey, I like unit model to work with and train my model for pixel classification or maybe land cover classification, while there may be someone else who would like to work with segmentation. And for those who do not know which model you should choose, we also have automated machine learning, where you have the option to just provide your data to the model using AutoDL and let this model deal with it. It will decide, it will basically evaluate different deep learning architectures and will figure out which one works the best on your data. Okay, so we have this API which does all of this. And within this list, there is a new model architecture, which is hyperspectral 3D RCNet. That's a unique one. So I'll just want to talk about it and show you a demo. So what's unique about hyperspectral 3D RCNet? It's a new kind of model architecture, which is unlike other model architectures that just could not handle volumetric and sequential data. This one can even capture spatiotemporal and spectral patterns. It can handle high dimensional hyperspectral data, and that makes it very unique. Because remote sensing data sets, we have a lot of them, but we don't have models that can really capture that information, that spectral information. And now we have one of them. So I'll just quickly show you a demo on how I solved land cover classification problem using 3D RCNet model. So in this example, you see this is one strip of hyperspectral imagery, and I had this ground truth data for the same, which is a land cover classification label. Now, what I wanted to do was train the model on this data, so that on the different areas of hyperspectral strips, I will be able to do land cover classification without needing to really train it again and again and manually digitize it, of course. And so how does that work? When you export training data in the classified tiles format, which is coming from the export training data for deep learning tool. So you go to this tool, you provided this raster, you provided this feature, that's the label, and then you ask it to just export it in classified tiles format. That's the format that's supported for pixels classification or segmentation tasks. And when you hit run, you will get data exported for this area. So that is what is called your training chip. Once you have training chips, you can open the train deep learning model tool, provide that here, and then select your model architecture. So within this, you can see there are different model architectures supported. And the new one is here, the 3D RCNet. So once you provide this 3D ArcGIS model architecture, you should be able to train this. However, let me also walk you through how you could do it through API. As I said, there are just 5 lines of codes that you could use to just automate all of your workflows. So you might not just want to do it manually over tools, but you may also want to do it through API. So here, if you see, we import prepare data, and then we import this model architecture that we want to use. In the prepare data, we provide this training data folder, the one that we exported through the export training data tool. We can provide that folder path here and simply do show batch. What data.showBatch does is it shows you how the exported data looks like. Okay, so if it looks nice to you, you kind of figure out that, yeah, it's kind of a land cover classification, small chips that the model should be able to learn. It's good enough to go ahead and proceed and do model instantiation. So here I am instantiating my hyperspectral 3D ArcGIS model. The next step is just call fit, model.fit. I have called it for 1 epoch to see how it works, and then later I called it for 5 more epochs, and when I was satisfied, I was able to save this model and see the results. And let me show you how it worked. I'm back to this, and if I just switch this on, do you literally see any difference in this? It just looks like similar to the ground truth, and these are actually the predicted results, and it's not the ground truth. So the model really worked within just 5 epochs of model training, and it was able to learn how to extract land cover classification over this hyperspectral, where there were almost around 200 bands of data that I had to train the model. But this worked out of the box. Next, I want to focus on remote sensing foundation models. You might have heard a lot about pre-trained models, but also something new, which is latest in the ArcGIS domain, which is remote sensing foundation models. How it's different from other model architectures or pre-trained models that you've just seen. It's really good. Trust me, it's really good. So I'll tell you how. Unlike the different backbones that you might have heard about, ResNet, ResNext, VGG, these are some model backbones that have been there in the market for like years and years, but they were trained on non-geospatial images. They were street level or oblique images that it was trained upon, and it had no spatial information. But now these remote sensing foundation models, when integrated as backbones instead of ResNet and VGG, for example, these new backbones, they are actually trained on geospatial data sets. So it has that spatial intelligence. It understands spatial structures. It understands spatial patterns. And so when you go ahead and solve your geospatial tasks, it really learns within just 30 minutes or 1 hour of training, as opposed to something else that used to take hours of training, huge hours of training. For an example, if you look at the screenshot, this is again the trained deep learning model tool. In the backbone model, you see here Prithvi. This is one example of the remote sensing foundation model that we have available. And there are more examples, for example, DOFA, Clay, and we are integrating these new models into these ArcGIS tools and ecosystem. So you could now utilize these remote sensing specific foundation models as backbones instead of relying on those non-geospatial ones. Of course, we love GIS. Next, I'll show you a demo on how I solved the rest of my problem on operational insights that I was talking about using just the remote sensing foundation model. So till here, what you saw was that I kind of got the results for building damage. I kind of got my route done. I kind of solved half of the problem, but there was a lot of debris as well on this imagery, and that needs to be cleared up. So to clear up this debris, I fine-tuned a model. So how do I fine-tune this model? I don't have a pre-trained model available. None of my existing foundation models on the Living Atlas worked well as well. So I went ahead and then I trained a deep lab model. I exported a training data with literally 96 training chips. So let me show it over to you. This is my debris classification training data. Let's view at this as extra large icons. And you can see these images that show these debris. And if I filter these by say type, it's just 96. with just 96 training chips, I was able to train this model with the backbone named Dynamic One for All, or DOFA. That's again a remote sensing foundation model, because of which I was able to train this on this model on this task, debris classification, within like 30 minutes of training. And you could see that I got really good results. And finally, when I performed inferencing using the Classify Pixels tool, these were my results. I literally got output as all of these areas and zones where there was debris clustered. And this can help officials really allocate resources and clear this debris up. Now, many of you might be getting started with ArcGIS API for Python, and this looks all cool. You can use notebooks, but how do you get started? How do you figure out what's my workflow? Is it same for every model architecture? Is it different? So to do that, we have ArcGIS notebooks as one of these offerings in ArcGIS Enterprise and ArcGIS Online, where if you click on this new notebook, you would see a couple of options. So there are these different standard, advanced, and GPU runtimes. Advanced with GPU runtime, if you have that, this is something I prefer because all deep learning models require GPU. So you could always use assistants now with notebooks and try to figure out what do you want them to do. So for example, here, I go ahead and proceed and type in, how can I use deep learning? And when I generated that, in the interest of time, I'm just going fast forward. And look at this. It literally showed what I was actually showing you a few minutes back on my notebook training. How do you import prepare data? How do you import deep lab? How do you train the model? And you can just simply add this to your training notebook and could still use that. So this is one example how you could get assistant's help to start writing your code. Now, there is also a templates capability available with ArcGIS notebooks, where you can just go ahead, select the kind of template you needed. For example, here I need a deep learning template. You click and see one of those. So you could either decide to do classify objects task, you could decide to do classify pixels task, whether you need to fine tune, as I showed some examples of fine tuning. You could decide what task do you want to do, and then go ahead and extract that template, and that serve as a starting point to your workflows through automation and APIs. With that, I'll pass it on to Pavan, who will next talk about 3D deep learning.
Thank you, Priyanka. Okay. All right, 3D deep learning. For 3D deep learning, we have point cloud classification as well as 3D object detection. To support them, we have couple different model types. And I believe at the moment we have 3 pre-trained models. I'm having a little technical problem here. Yeah, I can do that. Next. Here are some examples. This one is building point cloud classification. Another example of point cloud classification for traffic lights. This one is object detection, in which I detected these cars and the output is multi-patches. And another example of 3D object detection where we used object detection. Next. So here we are showing you a 3D point cloud classification. It is not new. It has been there for some time. Next, I'm going to show you this 3D object detection. Like I shown you in the previous slide, these are multi-patches for the cars in a parking lot. Just like imagery, we have dedicated tools for 3D workflow. So the first tool that I'm going to show you is prepared data. And this is pretty much like the export training data tool for imagery. Here I use this tool to prepare training data. Next, I use this dedicated tool to build a model. Of course, you have noticed that we are using a clip because it's very difficult to really show these workflows live. Once after the model, I detected these the cars, and here is the final result. And on the next map, I'm going to show you the 3D object. Actually, we can skip this next one. We can end it. Deep Learning Studio is next. It is a native cloud-based app. I think the main thing I wanted to highlight for this is it is enterprise level. It provides high scalability, and we have a dedicated session tomorrow morning. And if you are interested in that enterprise level scalability, please attend that. The other aspect is you can divide the work between teams, and it provides pretty much everything that is provided in ArcGIS except for this enterprise level, cloud native, these aspects. Next, we wanted to talk about third-party integration. Next slide. When we talk about third-party integration, usually like you have models somebody created. Most likely those models are hosted on Hugging Face. Priyanka has talked about how pre-trained models create bridge between Hugging Face models and ArcGIS. The other aspect is these models might not be shared on Hugging Face, and for which we provide full documentation and support for Python for these models. And I don't know if you can see, but on the screenshot, I provided a URL for GitHub repo where you can download this. You can see the sample and build your own Python raster function to use models. Next, third-party training data. This has been coming to me quite a lot. People have built training data elsewhere, and now they want to use in ArcGIS to build models. What we do next? So this is the way I personally do use these third-party training data is I write Python script. And I'm going to use this example where I'm going to talk about object detection example. On this image, what you see is a 600 by 400 image and a label. The label is in Pascal VOC format, and the numbers are top left and bottom right corners define this box. And all numbers, this information go to XML file. Instead, YOLO, on the other hand, is another popular format where the box is defined by slightly differently, the box and the height and width of the box. All numbers are normalized and the information is written in text file. And COCO is another popular format. The way they define the box is different, as well as the information, all the information goes in one single file. By now, you might have guessed that, like, hey, it seems like simple math, and reading XML file or text file and then converting to the format that Esri or Pascal VOC likes. We have written this blog, and Let me see if I can quickly go there. Oh, sorry. Could you go open this in browser? No, that won't work. So I'm not gonna run it, but maybe I'll try. So pretty much the same information, distinction, difference between the different type of popular object detection. I include example of Azure Machine Learning Studio as well as TensorFlow records. And these are Python script that we have shared on ArcGIS Online. And these comes with full documentation. You can download them. And the script also comes with sample data, so you can just literally run the script. I'm just going to quickly open and so what it does is like first, because like if you remember, this one is YOLO, and YOLO normalized the values. So I need to read the image dimension as well. So I get the image and read the dimension. Then I use simple mathematical formula to convert the numbers so that I can transform YOLO numbers to Pascal VOC. And finally, I write them in XML format. I'm not going to run this, but once the labels are created, I can replace newly created labels and just input the data in trained deep learning model tool. So that was an example of third-party integration. Priyanka, now let's look at the embedding one.
Okay, so I think that summarizes this session. In this session, we have seen how ArcGIS has powerful deep learning capabilities, be it ArcGIS Pro, ArcGIS Online, and ArcGIS Enterprise, be it ArcGIS Python API, and also how we can support end-to-end workflows from data export to model inferencing and at scale. We also saw a lot of pre-trained models. We saw how we could use GUI and desktop experience for GIS analysts and can solve a lot of problems such as operational routing in our case. And then how using notebooks and APIs, we can automate all of these workflows. With that, we end this session. Thank you so much, everyone. And we can take up questions next.
We can take your questions now. Yeah.
Bothered you about fine-tuning stuff before, but I'm just wondering, like the root damage model when you were fine-tuning it, did you match the training parameters that were used for the user uploading this model?
I did. You do not need to match that up because what learning rate finder does is it kind of deduces the best learning rate on your data. And because it's random initialization, it's always best to rely on the automatic learning rate finder.
And then like number of epochs did like checkpoint.
I did. So the question here is when fine tuning something like a roof detection, a roof hole delineation or a roof decking delineation model, when we fine tune from an existing model that exists on Living Atlas, do we keep same parameters? How do we checkpoint when when we need to stop? So when you go ahead and fine tune, how it works is that the ArcGIS API for Python already takes care of the automatic learning finder. So you don't need to worry about the previous settings. It would automatically pick all of that from the existing EMD file. And when you train the model, you can only provide early stopping equals true through the API, or when it's through the tool, you can provide early stopping equals true through the checkpoint. And when you do that, the model automatically stops when it stops learning. Yeah. Yes.
You're like fine-tuning them on model text. This is an example that we train extraction. How big your training data set has to be.
When you're fine-tuning,
If I'm trying to apply that like a whole scheme,
mm-hmm.
block should I do in So how big should my training data set be? And also, should I classify every single rooftop, every single building within that given area, or I could just pick and choose?
Okay, yes, that's a very great question, because this is something where we all get stuck. So, and I got stuck too. So I'll give you some background to it. When we try to fine tune a model that already exists, one thing is that if it needs to be scaled up to an extent which is larger, maybe a city or a country level, you need to ensure that the data is generalized, is still covering all the different types of terrains, right? So it's not that, the model that was trained on previously an entire US geography and you want to try it for China, for example. Now for China as well, there are different terrains. So you need to either make sure that you cover, because you're trying to work the model out for the entire China, you need to ensure that you pick labels for different smaller extents that cover the different terrains. And when you kind of create labels in this specific area, because the model has the tendency to learn the background as well, you have to ensure that wherever you create a label, all the labels around, all these similar features around the same area should also be labeled. For example, if there is a building labeled right in an extent and you miss out another label right adjacent to it, that serves as a background and the model gets confused. Hey, one place you say that's a building, the other place you don't say that's a building. So that confuses the model. So whichever extent you pick, you make sure all of these labels polygons are labeled in that area.
Rather be better to do the whole, like for that
Yes.
extent, every single feature.
Yes, exactly.
Choosing a larger extent.
That's correct. Choosing a larger extent does not help. That is why I was able to train good model with just 100 training chips or less than 100 training chips. Is why, because I literally labeled every single thing that was around within that area, and I did not want to go ahead because the labels look similar in all the places. Debris looks similar, right? But as opposed to something else that is like building roof detection or something that changes with terrain, right? If that changes with terrain, you have to ensure that that's part of your training data so it learns better. You're welcome. Yes.
Yeah, so the question is how Esri is deciding which model to build, business case, right? And it's more like user pattern. If we see, like, first it is sort of like we try to talk to people and ask industry like what they are interested in, and also users put ideas on ideas portal as well as on Esri community, and if we see a lot of traction, we work on the model. Besides that, we have a running list of sort of our own wish list, like what pre-trained models we want to build. And based on our resources, we decide where to work. But if there is a high demand, we will work on that rather than our what we want to do. Does that fully answer your question? Okay. I wanted to go back to the fine-tuning question. So we do have a couple of blogs, as well as there is, I believe, a sample notebook or tutorial sort of. In that, you can look at it. So the model build, that one is for building footprint, and the model is in that example. Model is for the US, and that model is fine-tuned for Middle East, where the architecture, landscape, everything is different. And in that example, you will see it's not big, it's a neighborhood. So it's not really like neighborhood versus city. Then if we talk about pixel resolution, it could be big. Usually what I do is like, I mentioned it like it's iterative process. So like I start with like quick prototype and then keep improving on that. I would say like about 500 chips should be good enough to start for a project.